Hello everyone, it's November 28th. Alright, go right into it. All paths from source to target. This feels like something that I've done before, but yeah. Oh wow, look at this. Back in July 2020, I have what, 4 different methods? Jeez. Alright, what do we have? Given a DAG of n nodes labeled from 0 to n-1, find all possible paths from node 0 to node n-1 and return them in any order. Graph I is a list of all nodes we can visit from node I. Okay, so 0 can do 1, 2, 1 can do 3, 2 can do 3, 3 to nobody. So it feels like just all elements are unique, guaranteed to be DAG, which means it will be a DFS. All right, DFS shall solve this problem. Maybe BFS might work as well. Let's go DFS. So DFS, we have a starting position, right? And then we find all its neighbors. And then when we find all its neighbors, for each one, we'll find all its neighbors until we hit the target. And as we go, I am pretty sure we can do the memorization. Wait, can we do memorization? Well, it's a DAG, right? Probably not. I don't think we can do memorization because the path from each node is dependent on what path has led to it, right? So we have to also record the path, right? And if during this any path has been visited, then we have to mark it, so we don't go back to the same path. But will we go back? Well, we might go back, right? We might go back. 0 to 1, 1 to 4, right? And then 0 can do 4. So no. And there will be no self loop, okay? So there's no self loop, which is fine. So we simply just have a path, right? And if, yeah, I think a general DFS shall work. I mean, we've done this before, so I'm pretty sure DFS will work. So we're looking for DFS with, actually we don't have to backtrack. Do we need to backtrack? We don't need to backtrack because it's not necessary, right? It's not necessary to backtrack. We just kept a path, right? We just keep a path going all the way, and that should be good enough. So basically, we're gonna call DFS, right? And we can say node, and we have a path is a list of int, and we have visited. Oh, then visited needs to be, that's gonna be a set. Right? Visited is gonna be a set of integers. So visited needs to go with backtracking. Yeah, so this one will return none, right? And then when I say res equals this, we say if node is equal to where is n? N is graph.length. So res is equal to this. Okay, we'll call n is equal to length graph. So if node equals to n-1, then res.append path. Oh, do we need visited? Let me think. like say for 0, I go to 4, right? And then I go to blah, blah, blah. And then I can go 0 can go to 1, 1 can, so 0 can go to 1, 1 go to 3. So the point is it possible that as we go in, we'll come back to the previous one? Acyclic, because it's acyclic, right? It's acyclic, so there'll be no circle, so it doesn't go back. I think that's what it means. It's acyclic, so there's won't go back. So if that's the case, then we don't need visited, right? This is not necessary. We simply just keep adding to the path, and that's it. And we're gonna copy it, right? So if this and else, we're gonna say for child, not child, for neighbor in graph node, neighbor in graph node, right? And then I just do the neighbor. But in that case, shouldn't we say like I do 0, 1 to 3, and I could go 0, 1, 2 to 3, right? So we all end up with 3. So from 3 going forward, because it's acyclic, so 3 can never go back to where it came from. So I think we can cache it. I do think we can cache it. Huh. I think we can cache it. That's what I think. Well, if we can cache it, then this one will return a list of int, right? If we can cache it. Yeah, this one we can cache it. So if this, I simply return node, right? Else, we're gonna say res equals this. For neighbor in graph, we're gonna DFS neighbor, and this neighbor should give me a list. Actually, it's not gonna be. It's gonna be a list of list, right? So DFS will give me a list of lists. Is all the paths from the current node, from the neighbor to the target, right? So what do? We say we're gonna we can say like deconstruct it. Right, we can deconstruct it. We can just like say for path in this res, right, dot append node plus path. And this is just going to be this. So for everything, we go everything, right? And once we're done, we just return res. And because of this, I don't need res. I just need to say return DFS, well, 0. We'll start from 0. Let's see how this one works. And actually, with this, we can go func tools import diario cache. I believe we can cache it because it's a DAG. So let's see, graph is this. Well, that's what I think. All right, and then the output is this. Now we pick the more complex one. This is the easier one. All right. And then we have the simpler. Let's consider like, I think this is considered the one of the edge cases. What else? All right. And this is the graph. And this is all path graph. And let's sort them. So say sorted, right, equals sorted answer. Yeah, and they all pass. I'm pretty sure this is it. I mean, I probably can make this one a little bit easier, like a one line instead of 2 lines. How would you do that? I can say, if we can reduce it. Actually, it's not reduce it. rest.append. But we can also do rest.extend. We can say rest.extend, right? And then this is going to be for path in DFS neighbor. And each path, we're going to just say node plus path. And we're just going to extend it. So save a line. Yeah, save a line. And then return rest. I mean, if you want to do this, why don't we just, can we put this one inside as well? For neighbor in this, and for path in this, then that will be, no, I like it this way. I like it this way. This is the amount of complexity that I think is still readable. Right, it's still readable. Yep. So I do think cache make a little bit faster. So this is LeetCode 104 797. So DFS with cache. Oh, and oh, what is the runtime? Well, every node will be visited, right? So that will say is on because every node will be visited. And as we visit it, we also have to do this, all right? So I think technically it's on squared. I think it's on squared. How many do? Yeah, 15. I think it's on squared. Depends on how many paths we have. I mean, every node we have visit, right? And for each node we visit, we have to visit all its children. And then for each one of them, we have to do this. Right? This will cost. I think this one costs ON, so that's why I say it's ON squared. Anyway, we run at 04, and so 53. I'm not in the mood of trying other things. Let me just take a look at what do I have in the past. I'll take a look at discussion. That's 1 year. I have DFS. If this, I had our append, and I have path, I have all paths. The next node, path.append. Now we go for the next one. And once we're done, path.pop. So this is backtracking, right? This is backtracking, okay? Very straightforward backtracking. What is this? Oh, it is now cache. This is my this is the idea, right? This idea. Oh, we don't need else. That's true. We don't need else because I already returned. So save another line. And this is the same idea. The next node, for path, if path. Huh? Why would it be if path? Huh. Path.expand, you extend, it's the same thing. Yeah, so this does not consider because you don't have to. What about this one? Consider cycles and does cache. Path node. Path. I create this destination plus 1. Path destination append. No, we don't have to because it's a DAG, so there's no such a thing, right? There's no such a thing as a node as visited before. We don't have to consider that. Backtracking. This is pretty standard. Backtracking should be I think the most standard. VFSI path. Let me do this. Yeah, it's very standard. But like this one does not have backtracking, so we do path plus, so we don't have to pop. 2-line recursion. Time complexity is 2 to the n. Oh, yeah. That's not n to the 2. It's 2 to the n. I'm not good with this time complexity thing. Why? We have n linked to n minus j. There are 2 to the n minus 2 paths. 2 to the n. We have n nodes, label 0, 2. I think of it as an array. For each pair of nodes, there be an edge. So there are n squared number of edges. Now we want to calculate how many paths there are from the 0th node to this node. Each path of length k corresponds to some choice of k minus nodes between 0 and this. 2 paths of length 2. There's a path of length 3. How many paths of length k will be n minus 2 choose k minus 1? That is true because we can pick any k minus 1 nodes between 0 and n minus 1. The number of paths is the sum of n minus 2 choose k for k equals 1 to the sum is 2. Okay, that makes sense. That makes sense. That's the worst case scenario. Is everybody has connection with everybody else. So we're going to start with a path of length 2, all right, and path of length 3. So just can't take any. All right, so all the way to path of n minus 2. All right, the total is n, and this is like 1, 2, 3, 4. 4 minus 2. 1 to 3 minus 2. So n minus 2. So total will be, we can choose n minus 2. So it should be n minus 2 choose k minus 1 of length k. Yes, it's true. A minus 2 choose k minus 1. And then k can be 1, which means it's path of length 1. So directly go there, right? And 2 all the way to n, and then we add it together. Yeah, this is good. I agree. Okay, that's for this. Let's roll another one. Yeah, go for the worst case scenario is the one to compute the complexity. I agree. To go for the worst case scenario. Ah, come on. Now we go back to the slow loading. This is super slow. Oh my god. Come on, let's do this. Come on, come on, come on. There we go. Oh. Alright, so I think we go on page 4 now. Corresponding. I click 4. Alright, now we have it. So we done an H index yesterday. And then, okay, how about this one? Find the duplicate number. Isn't that the same? Find the duplicate. Oh, wait. I think it's everything is repeated one time, and one value is repeated 2 times. Do you remember the other one? How the other one is solved? I don't. I don't remember how the other one is solved. I remember it's very complex. It's very complex. I remember it is. How is the other one solved? Counter. I think the other one solved is by representing every value in a bitmap, right? We just keep counting. Anyway, so this one is array of nums containing n plus 1 integers, where each integer is in the range of 1 to n. There's only one repeated value. Return this repeated value. You must solve or modify without modifying the array, and I use only constant extra space. So otherwise, it'll be easy, right? We just do a counter, and that's it. But now, maybe we can do the same one, right? At least one must exist in nums. All the integers num appears only once, except precisely one integer which appears 2 or more times. Oh, 2 or more times. One repeated number. Return this repeated number. It can repeat 2 or more times. Yeah, because if you want to modify it, it's easy. You just put everything in its supposed position. And if that position has already seen a value, then like this one, 1 is good. 3, we try to put in 3, and I will swap with 2. And 2 is good. 4, 3 is good. 4 will be, hold on, so 3 we will swap 3, right? Swap 3, and then 3 will come here, right? and then 2 is good. This one will swap 4, and 2 comes here, is no good. Wait, no, hold on. 0, 1, 2. 2 will go, and then we'll swap 2, and then 2 will swap again. So that's how we can know it's duplicate. What is the method we use? I remember that day, right? It's very complicated how we try to solve it. N is 10 to the 5th, right? 10 to the 5th is within 32-bit, right? Two to 31. Yeah, it's within 30. So I think it's bitmap. How do we do bitmap? I forgot. Jeez. I forgot how bitmap works in this. But maybe not bitmap. Because this one, we have integers, and it's 1 to n inclusive. Yes. Hold on. So it is possible to do, let's say return, I don't know, it doesn't matter. I think it does say we can do more than 1 time. More than 2 times. This one shall return 2 as well. Yep, this one shall return 2 as well. Counter, right? I think the key point is a counter. So we have a bitmap for each value, right? And then as we go through, we have what is constant extra space. Constant extra space. How is that constant extra space? How many counters do we need? 32 counters, okay? We need 32 counters, each one corresponding to each bit. Each one corresponding to each bit. And everything when it comes, we can do some magic to increment the counter for that specific bit, right? So each one we will count, and then what? At the end, we have 32 counters, each counter corresponding to each bit, and then we know all these bits. Then what? I forgot. Now we know that all the other counter shall repeat, right? Only once. So what? Let's repeat. And eventually, the counter that does not have the desired repeat will be the one that we shall focus on. Yes, I think that's the gist. But I forgot how it's implemented. So each position shall count. So 0 we do not count. If it's 1, then we count, right? And if we count, because everybody else repeat a 1, so if we count 1, then we go back, right? We count 1, then every time we count 1, if we count 1, then we will revert back to 0. Right? If we count 1, then we revert back to 0. So eventually, what's going to happen? What's going to happen? What is going to happen? what's going to happen is, hold on, 1, 3, 4, 2, and 2, right? So if I have a counter, we have a value repeating itself, but we don't know how many times it repeats itself. So it can repeat however many times, but everybody else is appearing only once. Right? Everything else repeats only once. So some of these bits will have count of 1, but it might have count of 2. Well, we keep counting, and then whenever we finished counting, then we will revert. So if at that position, it shall always be 0, because at those positions, everybody will repeat the same number of times. So in those positions, everybody will repeat once. Everybody will repeat twice, and it will appear 1, 1, boom, right? And a 0, 0, and a 1, 1, boom. And then this position should be 1. And if another one comes in, and it will be 1. Right, so 1, 1, so 1, reverting 2, it reverts to 0. And the 1, then we'll revert back to 0. 1, and we'll revert back to 0. And then we'll have this value. It repeats itself, but it didn't say how many times it repeats. Right? If I say this one repeats, but still, because everybody else repeat once. Yeah, I remember how the other problem is solved. The other problem has requires that 2 repeats are co-prime, right? Yeah, it requires it's co-prime. So we can keep counting on one of them, and one of them like k times. So the rest of them repeats k times, and the target number repeats, let's say, p times. And we want k and p co-prime, and p is smaller than k. That's how the other one is solved. So we can just count to k, then we rotate back to 0. We count to k, rotate back to 0. So at the end, the bits that are representing the p repeat numbers will have those counts not equal to 0, right? They will equal to p. So that's how we can find it. And that one requires 32 counters. And yeah, like if we don't do the fancy bit manipulation, we need the 32 counters. So that's that. But this one's different. This one is everybody repeat 1, so the k equals 1, right? If k equals 1, that method does not work, because we want k and p to be co-prime, but now, and then k needs to be larger than p, but now k is definitely smaller than p. So it's a completely different story, and we don't know what p is. See, this is a different problem. Okay, but we do have more clue, and the clue is containing n+1 integers, where each integer is in the range of 1 to n inclusive, right? But still, we have no idea which one is repeating multiple times. Okay. That is fine. That is fine. Yeah, I think the thing is just we don't know how many times it repeats itself. Alright, if I know how many times it repeats itself, this might be slightly easier. Yeah, if I don't know how many times it repeats itself, then on that counter, we know it at least repeats 2 times, right? At least repeats 2 times. But how do we know? In any given position, right? If in any given position, yeah, I don't know. I don't know the number. I don't know the number. I just have the range. Each integer is in the range from 1 to n, right? And nums contain n plus 1, so definitely we'll have repeats. But that's a good question. Very good. We cannot modify, we cannot do any things. Some value are unique. Some value repeat itself. Feel like this type of question, it still feel like a bitmap to me, but how do we do bitmap on this? Like we can count? Okay, let's say we count. We count on the number of, so some bit will have 1, some bit like this bit has 3, this bit has 2. What does this mean? Right? And then we have a total number is n. Like let's take a look at this. Right? 1, 2, 3, 4, 5. 5 values. Right? 5 values. And 5 values. If there's no repeat, okay? So let's say 1, 2, 3, 4, 5. That's 5 values. 2, 3, 4. Hold on. We have containing n plus 1 integers. All right, so we have n plus 1 integers. So if n equals 5, right, then we need to, no, n equals 4. N equal to 4, and we contain 5 integers, but n equal to 4. Right, n equal to 4, so we have 1 is duplicate. So let's now consider the duplicate. Let's just say n equal to 4, 1, 2, 3, 4, right? There's no duplicate. What are some of the, no, 1, 2, 3, 5, 1, 2, 3, 4, 5. What are some of the characteristics of these 5 numbers if there's no repeat? Right? There gotta be some characteristics that does not exist in the others. Well, in the others, I'd say this is 1, 3, 4, 2, 2, right? 1, 3, 4, 2, 2. If I exclusive OR the two things, then 1, 1 will annihilate, 3, 3 annihilate, 4, 4 annihilate, 2, 2 annihilate, right? So if I do exclusive OR, then the remaining value in a non-repeat, right? The remaining value in non-repeat will be exclusive ORing the value that is repeat, right? So the value is repeat will be exclusive OR with the value that does not exist. Okay? How would that work? Well, in that case, exclusive OR and exclusive OR and exclusive OR. Oh, what does that do? One, two, three, 4, 5. If I exclusive OR them, we get 1. How about 6? Or exclusive OR. So we can get exclusive OR value of all of them, right? So we get exclusive value of all of them. And then the current value given is 1, 3, 4, 2, and 2. So we're exclusive for them. Then what we have is a 5 will be exclusive for 2. Hey, that doesn't make any sense, right? It doesn't. Like the duplicate value is replacing some value in it. It's replacing some value in it. How about sum? So 1, 2, 3, 4, 5. We add them together is 15, right? And 1, 3, 4, 2, 2. So I 1, 2, 3, 4, 2. That add together is 12. So the difference is 3. All right. But that didn't solve anything. Some value is replacing. Right, some value is replacing. Man, I don't know. All right, any hints? Wow, I'm really bad at doing this. Related topic. Binary search, 2 pointers. Bit manipulation, similar question. Single number, first missing positive, set mismatch. Linked list cycle. Yeah. That's not helping. Binary search. You cannot manipulate the array. How do you binary search? One to n, right? So 1 to n, I can get a sum of 1 to n. And I can get the sum of the first n value to ignore the last one. Okay. All I can get all of them. Yeah, I want to get all of them. So for 1, 2 plus all the way to n. And this one we get all the values, which include sum, right? And then sum of this, and then have the duplicates. Like I'll have p duplicates. But actually we can do one of them, go back, so let's say p minus 1 duplicates, right? P minus 1 duplicates. And the other one is just 1 plus 2 all the way plus to the n. And if we do minus the 2, that will be the missing value. So we have missing 1 plus missing 2 plus all the way to missing p, right? Minus, well, actually it's missing 1 all the way to p minus 1 minus p minus 1d. So that's that, right? And d is a value from 1 to n. But m1 to p minus 1 we don't know. We don't know their value. No idea. But they're unique. No. No, it doesn't feel right. And the total occurrence is also, it's a hard sell. It will not be larger than a certain value. One, two, five, right? 1, 2, 3, 4. Well, actually it's 1 to 4. Right, if it's 1 to 4, but no 5. If I count, it should be 1 on the third position, 2 on the second position, and 2 on the third position. So if we count 2 on the third position, that means the repeated value is 3. Now wait, the repeated value is 4. Like 1, 2, 3, 4, 4. Then we have 2 on the third position. Okay? Now, if we have 1 on the third position, that means 4 is now repeated. Right? Okay, now we'll look at the second position. Second position should be 2, right? So, if it's more than 2, then we know that value has this. Oh, we might strike it. Yes. Yes, counter. Yes. We just produce from 1 to n, right? From 1 to n, we'll produce the counter for each position, right? How many times 1 is occurring in those positions. And then we do the same thing for the numbers, and we're going to find out, right? We're going to find out which position has more occurrences than what is allowed. And that bit must be set in the final value. And everything else will be 0. Let's do this. Yes, I think this one is right. Oh, excited. I'm excited. This one might actually bear fruit. And it is on, and all we need is 32. Now I'm not gonna do like a bit manipulation, I'm now gonna do the like a bit manipulation version of counter. No, all I'm gonna say is just counters, right? Equals 0 times 32. That is constant extra space, right? That's constant extra space. And, right, we're just gonna say for I, actually for n in range 1 to n plus 1. So we go 1 to n, and for each one, we need to turn that into a binary value. Well, it will be nice if we can. Nah, let's just do this. So it would be binary value n. Actually, that's not. Oh, this is bad. N equals len nums minus 1. Right? And for this, to n plus 1. And for each value, let's just do I here. We're going to binary this, and then we need to know where the ones are. And bin I, So what we can do is for, now we're going to use I. Now let's just do n. So this one is going to be 2 to the n, 0, 1, 2, because it's 0b, right? Because that's what I remember. If we do binary, like say 4, it's a 0b, 1, 0, 0. So we're going to do 2 to the n, so 0, 1, 2. And we're going to say for I, b in this, enumerate. Right, so when we enumerate this, and we say if, now we say counters something, will be plus equal to, b is equal to 1. Right, and then this is going to be, if we say 0 is on the leftmost, right? So 0, 1, 2, 3, 4. So it's going to be 32 minus I. I'm not sure this is correct though. So 0, 1, 2. That's actually, it's not going to be correct. The 0 is here. 1, 2. So we also need to know the length of the whole thing. Jeez, this is. Alright, no, I'm not going to do bin. I'm going to do. Isn't that f string? Right? F string 4, but I think we do. Nope, I forgot. Never remember. Python binary, no, int to binary. No, it's going to be int to binary leading zeros. I've searched this every single time I do questions like this. I never remember. The syntax. Keep leading zeros. Format works, but I know we can use f string for this. I just don't remember. Maybe it's a 4, and then we do 0, 3. Oh, almost. About B. Nope. Maybe 0B4. Nope. 04B. There we go. We got it. But if we can verify, let's format zfill f val 0 1 0. Nah, I think this is what we want. A 04B. So we need to just do. The whole purpose is to make it easier. All right, the whole purpose is to make it easier. So if this one will produce this, so we're just gonna do here f format and 032b, right? So if we go back here, let's say n equals 23, and we do n colon 032b. Yes. And actually, we don't need that much because n is 10 to the 5th, right? So 10 to the 5th, the largest is 10 to the 5th plus 1. And if we do log this divided by log 2, so 16. So a 17-bit. 17-bit shall be sufficient. So we can just do 17 instead of 32. Hold on. 17-bit. So it's 2 to the 17. And 2 to the 16 is not enough. 2 to the 17. So we do 17-bit. Right? And then here, instead of 32, we do 17 bits. So we're going to do IB, right? And then we say counter. There we can just say counter I. We don't have to compute anything. Plus equal to B is equal to this. All right? And once we're done, right? Once we're done, that is the counter. Oh, counter unique, right? Counter is unique. This is for unique. And we're going to do the same thing. We say, so on the counter unique, this was just counter. We'll do the same thing. We say for n in nums, all right? This is the same. This is not counter unique, it's just the counter itself, right? And then we're gonna build it up, right? We're gonna say for CU, for C1, C2, right? In zip it, counters unique and counters, right? If C1 is not equal to C2, we also need the I, this, in, enumerate this. If C1 is not equal to C2, actually we don't do it here. We're going to do it here. We're going to say, we're going to do a 0. If C1 is equal to C2, else we're going to do a 1, right? And the whole thing, we're going to say, right, dot join. I'm going to join this. That will be a binary string. And we're going to return int this. I think it's 2, right? So int, let's say 1111 and 2. 15, yeah. So return this. Okay. Now let's try this. We have a lot of test cases. Okay, this thing. This will be 2. So 3. 1 1. 1. 1, 1, 2, 3, 1, and of course I have. You actually keep going. Lots of 3s. 3. Okay, this is nums. Find duplicate nums. Go. All right, we have trouble. We have trouble. Okay, so these all pass, but the last one does not pass. What is that? Counter is fine. N is fine, and then we do all this. Oh, I should not go here. I shall go to the maximum. I think it's the maximum nums. There we go. It's the maximum num because you're going to include other values that can complicate things. So go maximum this, right? And go one by one. And then we count this, and do another counter. Okay. So this shall work. Try it again. Here. Yeah. Go. Wrong and ooh. Ooh. Really? 2, 2, 2, 2, 2, 2. Huh. Mark is 2, so we will do 1 and 2. Why would it be 3? Hold on. I think this probably is a bug instead of the logic. I think the logic is tight. I think the logic is tight. Right? It should be here. Oh, this and this. Good point. Okay, so now what? Dang it. So this position, we have more, so we know we have more on this position. But this position, it gotta be more, right? It cannot be less, right? It cannot be less. So we are counting on the ones that are more than we're supposed to be. And if it's a 0, that's fine. So it's not going to be equal to. If this is smaller or equal to, right, we'll do 0. Otherwise, we do 1. Now, what is C1? C1 is unique. Right? No, so if it's larger than, wait, no. C1 is unique, right? So if it's, yeah, it's a smaller than C2, the actual counter. What? If C1 is smaller or equal to C2. C1 is smaller or equal to. How? C1 is smaller or equal to will be 1. No, hold on. C1 is unique counter. If a unique counter is equal to or larger or equal to, there we go. Which I think is more intuitive is do this. If C2 is larger than C1, then we go 1. Otherwise, we go 0. Okay. All right, let's bring other things down. So basically, it's just the last line. We just need to change the last line. Yeah, let's just copy and paste the entire thing. Yeah, that is my mistake. Try it again. Very slow, but we got it. Very slow, but we got it. It is ON. Why would it be so slow? Well, because I have to iterate through everything. 2988. All right, we did get this one using ON, time, and O1 extra space. My idea is to count, right? To count the number of one bit from 1 to n without duplication. This is the baseline. Then we count the same thing, the number of 1 bit at each position, right? From 1 to n without duplication. This is the baseline. Now we count the same thing for nums. Right? We count the same thing for nums. Then we compare. Oh, we compare the two. We compare the two. Yeah, then we compare the two counts. If a position in the dupe count is larger than the non-dupe count, that position must be set in the actual dupe number. So this is ON, right? But this one runs really slow, 2,988. Jesus, 5% ranking. I mean, if you want fast, right? If you want fast, we just do counter nums, right? Dot most. I think counter nums has this counter. Oh, I forgot. What is it? The most elements most common. All right. N as omitted returns all elements in the counter. So most count most. And we just like say most counter 1, right? So we're gonna say this 1 0 shall work. Oh, I gotta return, man. Gotta return. Two and 8. Oh, I have to return. Wait, what's one return? Okay, so I have to go 0 and 0. Yeah, if you want fast, this probably will run extremely fast. but that's not the goal. The goal is to do it in O1. All right, time to look at the solution. I mean, it is possible to, I guess it is possible. It is possible? I don't know. I do need a counter. Unless we can do the counter part. Yeah, like depending on the number of, so it is possible to use numbers, right? So we'll have, let me try this. So instead of have an array for counters, we're gonna have 17 numbers, right? So it's gonna be like x1, x2, all the way to x17. And each one we have 32 bits, and each bit will count. And now we do the same thing as the other one. We just need to handle +1, which I don't want to do. Just, I mean, we can make this faster. We can make this faster, but we have to handle +1. But even if we handle +1, all right. 7 approaches. Jeez. Rearranging, modifying as do not meet the constraints. Feasible to come up at the first approach. Sorted, yeah, that's fine. Set. Negative marking. Flip the number at index 3. We flip. So instead of swapping, we can flip. Now when I flip index this, and then when it flip a 2, 0, 1, 2, in this one, already flipped. That's ON. 4.1 hash map. Oh, they want extra space as O1, and the time complexity is ON, but these change. I think the one that's most intuitive to me is, yeah, I won't do the negative marking. Negative marking is good. I will swap, but I like negative marking better. A set. Well, why if we do the set, it could just do a counter. All right. Let's see. Binary search. What? I was going to say, how do you binary search this? Or when log in. Sum of set bits. This is what I have. But I bet they do a better job than what I do there. Oh, when log in. Floyd's tortoise and hare. Hey, what? Oh. Wait. I'm speechless. Alright, we are going to take a look at this. How do you do this? Without sorting. And low high represents the range of the values, okay? Lowest one and high will get a current. Count equals sum. We're going to count how many numbers are less than or equal to the current. How many numbers are less or equal to the current? If the count is larger than the current. Hold on, let me think. So we're gonna see how many is. Wait, it didn't say it's sorted. Does it say it's sorted? It didn't say it's sorted. No, it's not. But we can still say, right? We still say the numbers that are less or equal to current. So if current, the value current, is, oh, how many numbers are less or equal? So it's the entirety. Okay, the entirety. If I given a current value and the numbers that's smaller, not equal, just smaller equal, shall be equal to me, right? If it's equal to me, that means I am not the duplicate. Makes sense. If it's equal to me, then I am not the duplicate. So I'll go higher, right? I'll go higher. If the count is larger than me, right? So I have the total count, and the count is larger than me, that means the duplicate is in the smaller side. So high goes down. Ooh, yeah. Good solution. Good solution. Okay, I try that. Binary search. I like binary search on this. Okay, this is a binary search from the official solution. Official solution. Okay. Put the link. Doesn't matter. All right. Of course, I'm gonna write a binary search my way, right? So I'm gonna say low high or equal to, low is 1. High is going to be len nums plus 1. No, nums minus 1. That's low and high. Or actually, usually expanded it will be easier, like this, which is expanded. While low smaller than high, all right. Mid equals low plus high, 2, and then s equal to sum, for n in nums, n is smaller or equal to mid. So we sum this up. We say if s is equal to mid, that means we're good. If s is smaller than mid, number of this is smaller or equal to me, right? Number of this is smaller or equal to me. So if s is larger or equal to mid, no, smaller or equal to. If s is smaller or equal to mid, right? That means the value, the duplicate value is higher, is on the higher side because we have less number that's smaller or equal to me, right? Less number. So in that case, we say low equals mid plus 1. Otherwise, we say high equals mid. Otherwise, s is larger. The sum is larger which we can actually do it here, right? We can say if this, right? If it's larger, right? If it's larger, that's more numbers than me. That means high will go down. And eventually, I think we can return low. But we're gonna try. This might not be right. Well, it's actually right. It's actually right. Again, I'll run this. Binary search is good. Binary search is good, right? So binary search, this one will be O and login. Nine 6, 17. What is like the high numbers? I don't know. All right, binary search is good. How about sum of set bit? I know, we just like count number of bits. Yeah, exactly. That's what I thought. But I'm pretty sure they have a better solution. Say the bit count difference is this. It's equivalent of the number 3. Huh. Yes. Well, more than twice, we just force it to be, or force it to be 1. Base count is this, 0, 4, 5, right? And this will be -1. So if it's -1, we always do it to 0. And 2, 3, we just go 1. Only including the bits with a positive count result. I think this is where the manipulation comes into play. To meet the constant space requirement, we'll consider 1 bit at a time. How many times the bit is set in nums? This bit is set. Yes, that's exactly my idea. All right, let's see. Duplicate n. I think they are doing the duplicate 1 bit at a time. N dot bit length. I can do that? What is this magic? N dot. Oh my goodness. Wow. N dot bit length. So instead of 17, I'm gonna say max nums, right? So we say max n equals max nums, and then this will just be max n dot bit length, right? And then this will just be max n, and then, oh, but how do you handle this? I don't think it's possible. So we just format. think we have to format. So format n. Hold on, we need to do this. Python into the binary leading zeros. How do we do on format? Format. So format n, and then we can say, so it'll be 017 b. Okay, so let's say m equals 10, and we can do f m. There we go. So that, yeah, you should use format. So in this will be format n f 0 something b. That something is max n. So we're gonna do the exact same thing here. Index out of range. That is because this one needs to be this. Still out of range. Oh, max n dot bit length. Unfortunate. We have to call this every single time. Dot bit length. The same thing. Dot bit length. I'm not sure. This might be faster. I mean, and also on this one, maybe it's possible to maybe like C2 minus C1. Yeah, that's fine. Let me try. Honestly, I don't think this one will make too much difference, but we can give it a shot. See, the majority is around here, 600. So we're gonna have update use bit length to reduce the counter size, right? Let's try it. Nah. It's even slower. Alright, it's even slower, but that's fine. Alright, let's see. So bits, so a bit in range. We have a mask. Okay. Base count, nums count. So for I in range n, everyone, if I, base count, if nums, nums count, and then if this duplicate, that is a good way to do the same. I like this one. So we don't have to produce this. We produce it along the way, and there's no conversion. Bit masking, no conversion. So this is 3. All right, well this we call it the official solution version of solution 1. The main difference is that this version does not involve converting numbers to binary. Instead, we use a mask to handle bit counting. which I think will be faster. So what do we need? So for this one, we need a dupe like this, a dupe, right? And then we just say for bit in, what would be the bit? So max n equals max num, so bits, bit length, right? Dot bit length. And then for bit in range, bit length, which means it's a 0 bit, right? Mask equals 1 left shift bit, and then for this first bit, for the 0th bit, right? For the first bit, I'm going to check every single one. So we have none dupe count is 0, and dupe count is 0, right? I say for I in range, let's say for I and in enumerate nums, say none dupe count plus equal to I and the mask, right? Which makes sense. If it's 1, that would be, oh, the mask, and it's not I and mask, right? It's not. It's if, yes, it's if. So when the plus equal to 1, if this, else 0. And dupe count plus equal to 1 if n and mask else 0. So we do all that, and then we say if non-dupe count is larger than the dupe count, then dupe all n mask, and then return dupe. Much cleaner, this solution. Ayo, fail. Okay. What the hell? What went wrong? Bitline is max unknown. That is true, right? And then this is for I. Oh, I think should be I plus 1. And nope. Anyway, the mask should be right. Right? The mask is right. I will be, actually it's 1 to n, right? 1 to n. Nums is n plus 1. Nums is n plus 1. One to len nums. That's 1 to n. And then we do this. And then we do this. What? Tuple and int. What? Oh, enumerate. There's no enumerate here. Nope. Nope. Well, len nums is n plus 1, so it's 1 to n. I is 1 to n. And for this position, right? And then for the current position, and we want to see if non-dupe count is smaller. Come on, man. Come on. Come on. Dude. Right? Dude. Can we combine these two together? Well, this one, if we go I, that's 0 to n. But we want 1 to n. Yes, fine. I'll just do it this way. If in, you know what? I actually think it's fine. We can do in, enumerate nums. We can do that. We can. Because I is 0, and then this one will give us 0. So it's actually fine. Yeah, so the situation, note that I goes from 0 to n. We want I to go from 1 to n. But fortunately, the case of I equals 0 is handled gracefully by I mask returns false. So that is a much better solution. I bet this one's faster. Gotta be faster. Come on, gotta be faster. Well, actually, it's not that fast. It's faster than my version. Actually, my version, because you have to do all the conversion. We don't have to do conversion. Now, remember, don't do conversion. Do bit masking. All right, I have one more solution to go through. Tortoise. I know this. This basically just, you go, one's faster, the other's slower. So how do we handle this? We build two numbers. So if it's a 2, we connect to 2. 4 we connect to 4. 3 connects to 3. And then 1 connects to 1. 6 connects to 6. 5 connects to 5. And 1 we do not connect anymore because I see. I see. Now we have a cycle. Goes to 5. All right, 2 to 4, 3 to 1. And then 1 connects to 6. 6 connects to 5. 5 connects back to 1. And we have another cycle. So we just need to find where the cycle starts. All right, and that's the duplicate value. Go twice as fast as a tortoise. Yes. It will be the first to enter the cycle and run around the cycle. A tortoise enters the cycle as well, and since it's moving slower, the hare catches up to the tortoise at some intersection point. Yes. phase 1 is over, and the tortoise has lost. All right? Yeah, it doesn't have to be, just some place. Here has traversed twice as many nodes as the tortoise, so 2 times distance equals this, implying f plus a times 2. So that's the tortoise has gone, right? So f plus a times 2 equals f plus n times c plus a. Right, the coordinate of the intersection point, f plus a equals n times c. And then remember, as I go back to, and then they go again, the point they meet. F plus this, the n times c. So if they go, tortoise goes here. And when it goes f, right, so the hare will go 2f, right? So a hare goes 2f, and then if it goes 2f, the hare starting point is f plus a. The position after f step is nc plus f. Oh, then they go the same. They go the same. Same speed. They go the same speed because that is nc, right? And then, so its position after f step is nc plus f. nc plus f. They meet at a cycle intersection, f steps. Tortoise started at 0. So in position f, it goes here. The hare started at the intersection point. F plus a equals n times c. So its position after f step is going to be nc plus f. Will meet at the entrance of the cycle. Yeah, I know this is correct. I forgot. I don't. This is not as convincing. Why from this to here is f steps? Well, because f plus a equals nc, which means f plus a can be 1c, 2c, 3c. Doesn't matter. So f plus a equals nc. So now we have a, then plus f, we must equal c, or 2c, or 3c, doesn't matter. So eventually we'll go back to c. That is correct, right? Because from hare's standpoint, it moves a from the intersection, and then if we go f, it will go back to, it will complete the whole cycle. So we go f, will complete the whole cycle. I mean, it can be 2c, so we'll complete 1 cycle and we'll complete 2 cycles, all right? We'll complete 1 cycle and then we'll complete multiple cycles. So yes, that's when it goes by. So tortoise first, and then break. Now we break, the tortoise and the hare is in the position, so we go from there. Oh wow. Whew. Ooh-wee. The tortoise and hare. My. What a interesting solution. Tortoise. How do you spell tortoise? Tortoise. Tortoise and hare. Dupe. Dupe signifies a cycle in the linked list. In the linked list that is created by linking the value at nums I to the value at nums I. Yeah, because it will go back because of the duplicate. It just means like if there's no duplicate, you can always swap, and everybody will be in place, right? So you can always go, eventually everybody will be in place. But this means you go, eventually you cannot force everybody to be in place, which means some value gets, duplicated, right? Some value gets duplicated. So we'll point back to a position where we have visited before. And from there, right, and then we go into the cycle. So when we say T and H, we start with 0 and 0, right? So TH, we start with all 0, and then, because that's their position. Wow, but the number is 1 based. Shouldn't we start with 1? If we start with 1, how do we go back to 0 position? This whole is n plus 1. So with the index is from 0 to n, right? Index is from 0 to n. So for any value, I will have another value. And now that value is 1. The value is 1 to n, right? The value is 1 to n. So the value is 1 to n. How do we handle the 0? We do go here. Yeah, just nobody goes here. This is the root. That makes sense. Nobody goes here. This is the root. Yeah, because it's 1 to n, and the whole array index is 0 to n. So it's fine. So tortoise and hare. And we say while true, t is equal to nums. What's the next one? Nums t, right? And here goes nums h. Let's just go one step. So nums t, that's the next position, so we go there. And then if t is equal to h, I'll break. Right? So that is, they meet each other. So now h stop there, t go back to 0. So t go back to 0. And we say while t is not equal to h, t equals nums t, h equals nums h, and when they meet, we return t. And we're good on some, but we're bad on some as well. How? Is it not the tortoise? Oh, shoot. Nums 0. Hold on. Let me think. Nums 0. That's our first position. So T and H are values. They're not indices. Grab a value, right? And then we go for the next value. Here T is in index, and now we get this value, and then we go to the next, and that is not index. Now, don't think T as index, T as value. That's true. T has to be value. These are all values. Now, if it's a value, then that's the next value, right? T, the next value is, we'll go grab the next value, and then this is the next value. And again, yeah, there we go. Tortoise in here. Very good. Uh-oh. We said it's a value. T is value, so we go one step. That is one step. Shouldn't do that. This actually turns out to be the fastest. $5.96 milliseconds. What's this 90% ranking? This is actually the fastest. They're the same. It's also ON time, and O1 extra space. Value. Right, T and H are the actual value. And then, because it's actual value, when we go to the next one, so that's just nums T. That goes to the next one, right? And then this is nums H. That goes to two steps forward. All right, will be it for today. Wow, we pick a good question. This is a very good question. Let's label it. I want to save this. It's not favorite. It's not really nightmare because we got it, right? We got it. Good interview question. This is a good interview question. All right, that'll be it. I'll see you guys tomorrow. Adios.